Okay, so now that we know what the identity matrix is, we want to move on to what is the inverse of a matrix. So if you have a square matrix of size n, a square matrix A inverse of size n exists, or could exist, such that if you take the inverse of A and multiply it by A, again, both ways, then you get the identity matrix back. That would be the inverse of A. So in order for a matrix to possibly have an inverse, it has to be a square matrix, first of all. If you have a 3 by 2 matrix, there's no way that that matrix has an inverse. And then what you have to show is you have to show that no matter what way you multiply it with its original matrix, that you get the identity back. It is possible to show that if you multiply in one direction and get the identity matrix, that multiplying in the other direction will definitely also give you the identity matrix. So in order to verify that you do have an inverse, that B is the inverse of A, you really only have to multiply one direction and show that you get the identity matrix back. Okay, that's something that we could spend time writing up a mathematical proof for, but I'm just asking you to trust me on that. And you don't want to do more work than you have to anyway. Okay, the word invertible means a matrix that has an inverse. So if I say that A is invertible, what that means is it has an inverse. Invertible matrices are also called non-singular. And if you see the term singular, what that means is a matrix that does not have an inverse. So some matrices have inverses, some don't. They have to be square in order to even possibly have an inverse, but even some square matrices don't have inverses. Okay, so first let's show, or I'm claiming, that these two matrices, A, I will call them, and B, are inverses of each other. So again, you're supposed to multiply them both directions and show that you get the identity matrix back, but we can just choose to multiply only one direction. So let's try the way that they're just given to us. Let's multiply A times B and show that we get the identity matrix of size 2 back from this. So we're looking to get 1, 0, 0, 1 back when we do this. Okay, so if I I'm going again across and down. So I'm taking 4 times 3 halves and adding that to 5 times negative 1 for my first entry. Then I have to take 2 times 3 halves plus 3 times negative 1 for my next entry. Okay. And then for my second column, I'm going to pick another color here. I do 4 times negative 5 halves plus 5 times 2. And for the last entry, 2 times negative 5 halves plus 3 times 2. Okay, now is when you want to grab your calculator out and have it do those calculations for you. What is 4 times 3 halves plus 5 times negative 1? What you're going to find is that gives you back 1. Feeling good about this so far. 2 times 3 halves is just 3, plus a negative 3 is 0. 4 times negative 5 halves plus 5 times 2 gives you back nothing, 0. And 2 times negative 5 halves is just negative 5, plus 3 times 2 is 6, so negative 5 plus 6 is 1. This is enough to verify that those are indeed inverses of each other. Again, what we now know also is that if we were to do B times A, we would arrive at the same answer. Okay, so that's how you check if you're given two inverses, whether or not they are inverses of each other. If you get anything other than the identity when you multiply, then they're not. How do you find an inverse from scratch? Okay, so to find an inverse of an n by n matrix A, what you want to do is join A on the left with the identity matrix of the same size on the right. Perform row operations until A turns into an identity matrix. The resulting matrix on the right will be A inverse. And it says after the row operations, if there is a row to the left of the vertical line that's all zeros, then the matrix is singular, which means you cannot turn A into the identity. Okay, so I already started this one. I gave all the intermediate matrices just to help the video go along a little bit better. But we're going to go through and fill in the necessary row operations. So if we want to find the inverse of matrix A, 2, 3, 3, 5, by using the augmented matrix method, notice I've attached it to the identity matrix of the same size. And then our goal is to turn the left side into the identity, and then whatever's on the right will end up being the inverse, if there is one. Okay, so let's go ahead and let's see. The first thing we want to do is turn this 2 here into a 1. And what I've chosen to do is not care about fractions. So I'm going to just do a half of row 1 and turn that into my new row 1. And I'm using my calculator. I've typed that in. I've typed this matrix in, and I'm doing my operations there. And I get the resulting top row. The top row I get 1, 3 halves, 1 half, and 0. So when you type this in, make sure you type it in as a 2 by 4 matrix, because you have 2 rows and you technically have 1, 2, 3, 4 columns. And you just sort of imagine that line in the middle there as you work this on your calculator. Okay, now we've got this leading 1 where we want it. We want to turn this entry below it, the 3, into a 0. So I'm going to do -3 times row 1 plus row 2, and I'm going to make that my new row 2. And again, I would do that step in my calculator to make this go a little faster instead of doing each individual entry at a time. And after we do that, our new row 2 will be 0, 1 half, -3 halves, and 1. What we've got there is we've got this first column now completed with a leading 1 and then the 0 below it. So our next goal at that point will be to turn this 1 half into a 1. Okay, so we can do that by taking 2 times row 2 and making that our new row 2. I'm just going to multiply that whole row by 2, which is sort of awesome because it gets rid of all the fractions in that bottom row at least. So my new row 2 is now 0, 1, -3, 2. And then the last operation we need to do is we need to turn this 3 halves into a 0. So I'm going to take -3 halves times row 2, add that to row 1, and make that my new row 1. Upon doing that, our new row 1 should turn into 1, 0, 5, and -3. We've successfully turned the left-hand side into the identity, which means what's left over here on the right-hand side is the inverse of A. So everything actually worked out really lovely on that one. Okay, let's try the same steps on this new matrix, matrix B. So I'm going to attach matrix B, 4, 6, 2, and 3 to the identity, 1, 0, 0, 1, and work on this to try to turn that left-hand side into the identity and see what happens on the right. So again, I'm going to not care about fractions, and I'm going to just say, let's take this whole row 1 times a 4th and make that our new row 1. That would make a 1, a 1 half, a 1/4, and a 0, while leaving the bottom row the same. Okay, let's now pivot around our leading 1, and let's change that 6 into a 0. We would do that by taking -6 times row 1, adding that to row 2, and making that our new row 2. That doesn't actually change row 1, so I just rewrite it. And that gets my 0 where I want it here. When we take -6 times a half and add that to 3, we also get a 0 here. And the rest of my row turns into a -3 halves and a 1. So because this happens, because you have zeros only on the left-hand side there, what that means is there's no way, once that happens to you, there's no way at all to get that other leading 1 that you need down there. This left-hand side cannot ever turn into the identity, which means we can't proceed, and this does not have an inverse. So there is no inverse in a case like this, and what we would say is B is singular.